We want to welcome Dr. Hummel here today. Again, thank you for coming and joining us for part 2 series. Last time she went over jump genomics with us, and it was a very valuable seminar for a lot of us because I had emails and feedback from everybody about it. Today she's going to talk a little bit more about basic split plot analyses, ANOVA models, go over a little bit of principal components if she has time. As usual, feel free to type in your questions, and then she can go ahead and tackle them as we have time. All right, I'm going to pass it on to her now.
Hi, thank you so much. Sorry, I clicked on the rename yourself button instead of the unmute, so hopefully I didn't rename myself. I'm so glad to be here again today and talk about this topic of mixed models. I'm going to show you some things, hopefully, that make it a little bit easier to figure out what model you need to run, and then I'll show you how to do those things in JMP. So it's going to be very focused on how to do this in JMP software, but I'm also going to spend a little bit of time on how to decide what model to run. So I'm going to share my screen now. And I think you are seeing my desktop.
Yep.
Okay, so I'm going to get started. We're going to talk about split plot analysis, BLUPs, how to pull those BLUPs out of the analysis, and then a little bit of principal components analysis at the end. And I'm going to show you how to do this in JMP. It's kind of important when you're talking about mixed models to know that there are two versions of the software, two versions of JMP. There's a standard version of JMP that we usually just call JMP, and there's a professional version of the software that we often call JMP Pro. So I'm going to show you, I'll be using JMP Pro the whole time, but I'll show you what you would do in standard JMP versus what you do in JMP Pro. We have slightly different platforms developed in these two softwares. So I'll point out all this stuff as we go along, but I just want you to know that there are two ways to do this even within JMP. Okay, so I'm going to walk through an example of cotton breeding. And the idea of this experiment is that we've got a field, and in the field we have 8 large plots that we can use for this experiment. And we have 2 genotypes that we want to plant on these 8 large plots. So since we have 2 genotypes, and that's our main factor, factor A, I'm going to call that in the language of sort of textbooks, but genotype is the factor A for us. So we have 2 genotypes, and since we have 8 plots, that means we can get 4 replicates for each of the 2 genotypes. So this is at the simplest. This is a simple experiment right here. We have 4 replicates for each of the 2 genotypes. So I'm going to just take a moment, and we're going to bring the data into JMP, and we're going to pretend this was our whole experiment. It's not. It gets much more complicated. But if this was our whole experiment and we're bringing the data into JMP, I have the data initially as an Excel spreadsheet. If I open this, this is what the data look like in this Excel spreadsheet. And so it's some information about some extra stuff we haven't covered yet. So the genotype, there's 2 genotypes in this list. We haven't talked about how year is going to play in yet. We haven't talked about sampling techniques yet. We haven't talked about, oh, we did just talk about replicates. So this is our replicates 1 through 4. And then we've got 4 responses that we're going to look at. I'll just look at strength today, but I'll bring in all the data, and we could look at this many other ways. There are multiple sheets in this Excel spreadsheet. I could delete the extra sheets, or I could just bring this in and let sort of JMP figure it out for me. So this is what my Excel spreadsheet looks like if I go to JMP and open JMP. There are a bunch of ways to bring files into JMP. One of them is using this JMP starter window where I go to File and Open, but I'll just use the menu bar from the top and go to File, Open. If you heard me speak on this series a week ago or 2 weeks ago about JMP genomics, you would have seen me also using something very similar to this. And you may notice, if you watched that and you're watching this also, you may notice that I'm using a different operating system on this webinar than I did last time. Last time I used a Windows operating system because JMP Genomics needs a Windows operating system because it's calling SAS in the background. But I typically am a Mac user, so I'm showing you JMP on my Mac today because I'm not using the SAS components. I don't need the JMP Genomics components for this, so you can see JMP works on both Windows and Mac. If you're using the Genomics SAS components, then you actually need to be running it on a Windows system or some kind of Windows system environment within Mac. So you're seeing my Mac today. On Mac, the window, the menu bar is along the top of my window because that's how this operating system works. If you have Windows, you'll see that same set of options: file, edit, tables, rows, columns, DOE, analyze, graph. All that stuff is going to look identical. It'll just be fused to the actual window boxes instead of at the top. So very similar. It looks really similar on Mac or Windows. So I'm going to go to File and Open, and I'll just point to that Excel spreadsheet. So split plot nk publish.xlsx is what I want. On Mac, I have specific options here, so I can click on options and ask for using best guess, using Excel wizard. If you have Windows, you'll have the same options presented in a slightly different way. So I'll say open, and I get this little wizard that helps me bring the data in. JMP is pretty smart. It recognizes the column names at the top, but if I had column names on a different row, if the column header started on row 2 instead, I could change this. And so now you see the first row of data becomes the column headers. So there's a lot of stuff I could edit or alter here. Also, if I wanted to, it discovered that only sheet 1 had data in it, but if I had multiple data in multiple sheets, I could select all and bring all of them in. So it's pretty easy to bring data into JMP. I can keep clicking next if I want to make sure that I do this correctly, or I can just click import if I think it's doing it right. So here's what my data looks like in JMP. Really similar to how it looks in Excel, but we get the extra things like I can save scripts, I can save my work up here in this corner. I get these little icons indicating that some of this data JMP believes is continuous data. So that's not actually true for the reps. 1, 2, 3, 4 is not really continuous. Those are still categories, so I might call them nominal or ordinal categories. The year, maybe I'm treating that as continuous, or maybe I'm also treating those as categories. Some of these other data should be continuous, but they were brought in as categorical. So I can tell that by this, they're listed as nominal, and continuous isn't even an option. So this can happen when there's something like a missing value code that is not the same as JMP's missing value code. I think in this case it actually happened because I changed the first line of the data into column names. I think I messed it up in that way. So if I wanted to change these back to continuous, I double click in the column and I change the data type to numeric. As long as there's numbers and no characters in there, I can do that. And now it's going to be, I'll treat it as continuous data here. So now I was able to change that to continuous. I'll do this with the strength data. I change it to numeric and continuous. And you can see there were a lot of other options in there too, like I could change it to currency or date or time or geographic. There's a lot of ways I can sort of carry the unit measurements with these numbers, or I can change the decimal points that are viewed. Lots of stuff you can do to clean up your data right away, but we're going to get into the analysis. So this is what my data look like. I'm going to close this one though, and we're going to work with a data file of the same data that I've already prepared in JMP, because I've got some scripts saved in this top left-hand corner, this factor A and B, and third. These are poorly named analyses that we're going to go through. So we're going to start with that first analysis. So we've described a scenario where we just have 8 units. 4 of these will be replicates for one genotype, 4 will be replicates for another genotype. But we actually have 240 rows of data. So when I run this analysis, it's not exactly the correct analysis yet. So what I'm going to do is go to the Analyze menu and Fit Model. So whether you have JMP or JMP Pro, you're going to go to the same place, the Analyze menu, Fit Model. And from Fit Model, I know that I want the strength to be my Y variable that I'm looking at. So I'm going to be fitting a model for strength. I could do this for all of the variables as well. So I could choose the other guys as well. And I could fit the separate models. So I could click this fit separately and fit all the models for each of the responses at the same time, but I'll just do one at a time so we don't have as much output to dig through. So I'm predicting the strengths. And the model I have so far, genotype is a fixed effect. So I'm going to add that into my model. And I also have that replicate. So if we skip back to the slides, we've got the genotypes, 2 genotypes over these 8 plots, and the replicates. So what I really have, if you can ignore the bottom line, the residual line, what I really have is factor A is applied to these plots. That's our genotype. Then I have replication, so 4 replicates. The genotypes are a fixed effect because I actually care about the specific genotypes. The replicates are a random effect because I don't care about the specific replicate. Replicate 2 means something different in one experiment than it means in another experiment, but the genotypes are a fixed idea moving from experiment to experiment. I care about comparing one genotype to another genotype, don't care so much about the replicates except to explain their variability. So genotype is fixed, replicate is a random thing, and then if I only had these 8 experimental units, then my residual error would be the genotype by replicate. So if genotype by replicate looks like an interaction term, but it really means each genotype has 4 replicates. So if I tell you the genotype and I tell you the replicate number, you know exactly which one of these 8 subplots I'm pointing to. So if I tell you it's genotype DPL491 and it's replicate 1, then I'm talking about the very first time DPL491 shows up. If I say it's DPL491 replicate 2, that's the second time this shows up. So I can uniquely identify the experimental unit by the genotype by replicate. So that means that's the error term to test factor A against. If I only had those 8 experimental units, I wouldn't need to specify this error term. It would just be automatic because that would be the residual. But in my case, I actually have more data because there's more layers to this, so we're going to have more residual stuff. So at the moment, my experiment looks like I'm predicting strength by just the genotype. And if I only had 8 samples, this would be the whole model I'd need to run because the replicate would just figure itself out. But if I want to include the replicate and I want to include the genotype by replicate error term to test genotype against, here's where it matters which software I have. So when I want to start putting those random effects in, so I want to get replicate in there and I want it to be a random effect, and I want to get genotype and replicate in there and I want that to be a random effect. So when I'm using standard jump, I would keep this personality of standard least squares, and I would click on the replicate and this attributes and make it a random effect. So replicate now is a random effect. And when I did that, it asked me if I wanted to use the REML method, which it recommends, and you do, yes, you want to use the REML method, or I could switch to the expected mean squared traditional method. Don't do that unless you're trying to compare to an older textbook. The REML method is in general the best choice. I also get the choice about unbounded variance components or estimate only variance components. So if I only want to get the estimates of the variance components, I can check this. And unbounded variance components means that I could get that the replicate variance is negative. That's scary. It's scary to imagine that you would allow variances to be negative, which is what I'm checking. I'm saying, yes, allow variances to be negative, but that actually is the better choice. It's hard to interpret those, but it's actually going to fit the model better. So generally you want unbounded variance components checked and estimate only variance components, probably not. We probably want to fit everything in the model and have the most things we can compare. If I want to now get that genotype by replicate term into the model, I can choose the replicate from this list and the genotype from this list, or I can choose just replicate and genotype both in this list by hitting the control key. Any way I can get a combination from this column's list and this column's list, and then click cross. So that gets the replicate by genotype, and it also inherited that randomness. Because I chose something that was already random, it inherits the randomness like it's a disease. That's good. We want that to happen. If you have an interaction between something random and something non-random, it should inherit the randomness, that disease, from its parent. So if you somehow put this term in, let me delete it. If I'd put genotype by replicate here and cross them, it didn't inherit the randomness because I hadn't associated random with it. So then I need to go back in here and say, make that random. So I hope that's clear. We think through what terms we want to put in our model, and then we come over here to jump and we put those terms and make sure we assign and random with anything that's random. So I'm going to click keep dialog box open so I can show you how this will look different for Jump Pro in a second, and I'll click run. And this is what we get for this incorrectly specified, very simple version of the model. We get in the parameter estimates, we get the effective genotype, and we actually get one of the genotypes compared to the other genotype. So it tells us you're going to compare DPL491 to the other one. And here's the size of the estimate. These will make much more sense if we look at other types of output. So this is the p-value is probably the more important, interesting thing from this particular piece of output. This tells us, yes, there is a statistically significant difference in the strength of the two genotypes. And specifically the other one, not DPL 491, the other one is the stronger one because this was a negative estimate here. The random effect predictions, these are the BLUPs. So here's our list of BLUPs. If you want to really easily pull these out, you can right click on this table and you can say make into data table. And now you've got the list of BLUPs here if you needed to use them in another analysis. So we'll definitely use a technique like this if we're using jump genomics and we wanted to fit the BLUPs first and then put that back into jump genomics. So that's just right clicking and asking. So again, I just right click on the table and say make into data table if I want to pull this out into another jump data table. So this is where those BLUPs are. This is telling us that rep 1 had much lower strength on average than the others. Rep 3 had the highest strength. The rep by genotype BLUPs are here as well because that was another random effect. So I can see that here's a few. Rep 1 and 2 seem to have some higher effects. Yeah, so here's our BLUPs. And then we also get a table of the variance components. You can see the rep actually was negative. So that was the problem, that we were allowing negative estimates. What happened is that the variance is very close to 0, and we can fit all the effects better by making it slightly negative. So it just helps us fit the model better. So in interpreting, we don't want to say that there's a negative variance, but we might say that it's very close to 0, and so it's estimated as negative. In fact, the rep by genotype is also quite negative, or quite tiny. So we're going to find as we analyze this that rep effect does not have very much variation associated with it, which is wonderful. That's great. There wasn't some kind of pattern with the replication. Some other cool things that we can do here are to actually look at comparing the estimates. So we might do multiple comparisons. So multiple comparisons, we could look at the least squares means estimates for genotype, and we could look at the plot. If we had multiple comparisons, we're just comparing one thing to another. There were only 2 genotypes, but if we had multiple comparisons, we could choose multiple comparison corrections. So here's a least squares means plot of the strength of DPL 491 compared to FM 832. So we see the plot, we see the estimates, we see the standard errors and confidence bands for those guys, and we could also look at the actual tests between them if we wanted to. So that's the simple incorrect model. So now let's move to how we would do this in JMP Pro. So again, just with a simple model where we want genotype as fixed, rep, and rep by genotype as random. For let's take all these back out. Now, instead of standard least squares, we would choose mixed model. So mixed model will be an option for JMP Pro. So if I choose mixed model, now I get different tabs for the different types of effects. So for fixed effects, I just had genotype. For random effects, I had rep, and I had rep by genotype. So that's the difference in how I set this up. The mixed model personality is going to use the REML method. And again, it asks you, do you want unbounded variance components? I say run, and my output looks similar, but there are some slight differences in it. So again, the random coefficients, here's my BLUPs. And it doesn't give me all that extra stuff about the BLUPs now because it knows the mixed model personality is set up specifically for mixed models. So we can trick standard least squares into using random effects and using REML to do that. So for people with standard JMP, you can do this the way I just showed you and you can get the right kind of output, but the fit mixed platform is actually designed specifically for this. So we're going to kind of remove things that you wouldn't care about in the mixed context. So here are the BLUPs. They're called intercept here, but these are the BLUPs for the rep and the BLUPs for the rep by genotype. We see the same results. We see that there's rep number 1 had a very negative impact on strength. Rep number 3 had a very positive impact on strength. We see again the genotype estimate. So we should see the same numbers between the 2 platforms. Okay, so now let's move into a more correct analysis for this particular data. So really, we had those 8 plots, but we subdivided the large plots into experimental units, into 10 experimental units within each of the 8 plots. Now we're going to apply factor B. Our next factor is going to get randomized within the 8 plots in each of those big plots. So these 8 subplots get randomly applied with a different sampling technique for taking the cotton measurements. So these 10 different sampling techniques, which we're going to call sample, they're randomized within those large plots. So there's a different randomization for this plot for the 10 factor B factors than there is for the next big plot. So everything gets randomized separately. So now we're looking at an idea like this. We still have the genotype at the top plot level, and those had replicates associated with them. The genotype by rep is the appropriate error term to test genotype against. And then in the subplot level, we have the sample techniques applied. And then we also can test that A by B interaction. The genotype by sample interaction can get tested down here at the B level. We don't have any extra replication this time. We had those extra replications of genotype. We don't have extra replication of the samples. That's fine, not a problem. Just not going to include it in our terms. And then our error term at that subplot level is the genotype by rep by sample. So if, remember that in our simple version, we could identify one experimental unit by saying this was the genotype by rep. If I know the genotype and the rep, then I know the exact experimental unit. We do the same thing here. The experimental unit for the plot, the subplot level, for the lower level, is uniquely identified by knowing, here we go. So one of these is uniquely identified by knowing the genotype, the rep, and the sample method. That would tell me exactly which one of these little subplots I'm talking about. So that's now the error term for the subplot level, the genotype by rep by sample. So if we want to fit this model, we go back to Analyze and Fit Model. And I'm going to do this with the mixed model because it's a little bit easier with the two different tabs, but we could fit the same model in standard jump. We just would use the standard least squares, and we would use that attributes to get random effects. So very similar, but I'll use the mixed model because it's a little bit easier. So I'm going to use strength again as my response. I'm going to, in this case, let's move this slightly to the side so we can see them. So I need, I'll shorten this. You can easily wiggle things around in jump boxes. That'll be easier to see. So I want genotype to be a fixed effect. So let's get that in there. I might want to test the rep, and I might want to test the genotype by rep. I will make a decision later on. I think what happened in the published paper is that everything involving rep got knocked back out of the model because they were so insignificant. So we could put rep in, and we can put genotype by rep into this genotype by rep into random effects, but they probably are not actually going to be all that interesting. Sample is a fixed effect, so let's put sample in. Genotype by sample is a fixed effect, so let's put genotype by sample in. No replication at the subplot level, so nothing I need to put there. And then our error term for the subplot is genotype by rep by sample. So that goes into the random effects, genotype by rep by sample. So there's lots of ways to create these crossed things, but that was one of them. So here's our random effects, here's our fixed effects, and then I can run this model. Again, still not quite the correct model. We're getting closer. So all the variance components, we get the estimates. We have lots of negative estimates. Everything that has rep involved seems to be problematic. So that's why we might end up taking the replication term out of the model at the end. We see the fixed effect estimates. We see those random effect blups. Again, we can use the red triangle to do more comparisons. So we can do marginal model inference, conditional model inference, and just regular multiple comparisons. So let's do maybe the least squares means for sample by genotype with the means plot. Let's do an interaction plot where we put the sample. No, I'm not sure what I want. So I'll try sample first. We'll see. Oh, that was a good choice. So we're looking at genotype to genotype, the samples overlaid on top of each other. And again, we can, I think I didn't actually ask for the multiple comparisons test. So if we did all pairwise comparisons with two keys on a significant difference, for example, or if we compared everything with a control, then we could get the actual comparisons, the difference comparisons. And so there's a whole bunch of ways you can look at that output. So an easy visual is everything that turns red as a statistically significant difference, and you can hover over it and see which sample, which genotype those are compared to each other. So lots of ways to view this. Again, we still have the wrong model. So let's go back and add another layer to this model. So the last thing that we didn't talk about in this model is that, in fact, the same experiment happens 3 years in a row. everything gets re-randomized over those 3 years. So we've actually got that experiment with those 8 large plots subdivided into 10 small plots. That happens each year for 3 different years. So actually what we've done is create big blocks at the very top of the experiment, and then we did the experiment totally re-randomized within each of those 3 blocks. So let's look at our new table. Our new table puts block at the top. Whoops. And blocks often are treated as a random effect because we don't usually care about that specific block. I don't care about 2009. I want to know if these results will hold throughout the years. So I don't care about the specific year. I'm going to treat it as a random effect. So we're adding in year now. We already had genotype, but now we can look at the genotype by year interaction. That's going to be random because year is random, so it inherits the randomness. Then we also still, from before we had the rep and the genotype by rep, I'm putting these in italics because I think they're not really that helpful and we're probably going to remove them. Then we have the error term for the plot level, which is year by genotype by rep. So we had to add that one in. It used to be genotype by rep, but now we understand that it's actually year by genotype by rep. Then our factor B level was the sample. We already had that. Genotype by sample interaction, we had that. But now we can also include the sample by year interaction, and we can include the genotype by sample by year interaction. So these are all things that if we discover they're very insignificant, we may decide not to include them in the model, but we'll run a full model with all of these things first. Still don't have any replication at the subplot level, and so our final error term, our very bottom error term, is year by genotype by rep by sample. And that is actually the residual term. If we look back at the data table, we had 240 rows. Those are coming from the year, there are 3 years, times the genotype, there are 2 genotypes, times the rep, there are 4 reps, times the sample, there are 10 sampling techniques. So 3 times 2 times 4 times 10 is 240. So that is the 240 unique experimental units. So we finally have a model that goes through all of the levels, blocks at the top, factor A applied at plots within the blocks, factor B applied with subplots within the plots within the blocks, and at the very bottom, those experimental units that are the subplots. So now this model, this is what we're probably going to include. The year effect, genotype, genotype by year, maybe not rep, maybe not genotype by rep. Year by genotype by rep should be included as the correct error term for the factor A level, but we might even exclude that. We'll see. Sample, genotype by sample, maybe sample by year, maybe genotype by sample by year, and then the bottom level is the residual. So that final model, let me go back to the model dialog. That final model looks like this. We have the genotype effect. That was the factor A, factor B, factor A by B. For random effects, we have year, year by genotype, year by sample, year by genotype by sample, and maybe some of those things with rep. So maybe we want some of those rep effects also. And when we run this model, we see those variance components. At this point, by not including the rep things, we only have 1 negative variance component, so that's better. That's one of the reasons that removing the rep was really useful here. We see the fixed effects, overall estimates, but again, these are hard to interpret. It's easier to look at them as comparisons, so we might want to go to that multiple comparisons. And we get the random coefficients, which are the BLUPs. So here's our year by sample BLUPs, our year by genotype by sample BLUPs. So these are probably the BLUPs we'd really care about. Hover over it, right click, make into data table, and now we have a list of all of the BLUPs for that year by genotype by sample. Okay, so here's a good place to stop. I have a second simpler example of split plot just to sort of solidify the ideas we talked about. So I'll show that in a moment. But for this example, are there any questions on this example that you want to look at right now?
Any questions, anyone? I guess none. You can move on.
Okay, so I'll show you a slightly simpler example. because this one was a pretty tricky example. Ideally, I mean, in agricultural experiments and field studies, this is a very common type of analysis, and so you really do want to understand split and split plot designs, but they are tricky, and so we'll just sort of solidify this with a smaller example. So
Sorry, Ruth, there
yes,
is one question there. One attendee has their hand raised.
okay, great. I'm not totally sure how to check that.
Rob, can you read the question out? Because I don't see it on my end either.
Yeah, maybe. Omer, did you raise your hand by mistake, or do you have a question?
He said he doesn't have a question. He just
No?
typed it.
Okay. Okay, perfect. Sorry, Ruth.
Oh, no problem. And if anyone does have a question, you can ask at any time. I'll pause again after each little section, but feel free to interrupt at any moment if you do have a question. So this simpler example is I think this showed up in textbooks a number of years ago. I don't remember the original author of this study, but this is a study of cooking meat. And so it's actually turkey carcasses. It's the Monday after US Thanksgiving was this last Thursday. And so maybe this is an appropriate example right now. So the idea of this experiment was to test different meat tenderizers on cooking these turkeys. And so we had, I believe it's 6 blocks, so 6 turkey carcasses. Within the turkey carcass, so that the blue oval is representing the block, and we had 6 of them. Some experiments will have a block at the top, some won't. In our example we had a block at the top that was the year. Sometimes this will be the case, but it won't always. So in this case, we're blocking by 6 different turkey carcasses. Within those carcasses, we're taking 3 sections of meat, and we're applying the first factor at that top level to those orange sections of meat. So those orange sections of meat are getting a particular method applied to them, so a different tenderizer. So this orange section gets one tenderizer, this gets a different tenderizer, and this gets a different one. And each blue block gets those orange pieces re-randomized with so it's not that up by the neck always gets the same factor A treatment. You want to randomize within each block those factor A treatments. And then within the orange pieces, we have subplots, these little purple cores. Little pieces of the meat are taken and then they're cooked at different temperatures. So our factor B is a temperature treatment that's assigned to these little guys within the orange. So if you think about this, we have 6 of these guys. So let me see if I can make this. I hate using Word documents to do things. This is on the fly and maybe a bad idea. But we would have 6 of these guys. So 1, 2, 3, 4, 5, 6. So 6 of these guys. And within each one, we have 3 orange plots, and within each orange plot we have 4 little purple subplots. So if we think about this experiment, 6 big blocks, each one has 3 orange things within it. The experimental unit for the factor A, which is applied at the whole plot, the experimental unit would be one of these orange bricks. So if we have 3 of them within each of these 6, we have 18 experimental units to test that factor A against. And then we have 18 times 4 experimental units to test that factor B against. So at the top of the experiment, we have the top block. It's random. The degrees of freedom should be the number of blocks minus 1. The fixed effect is factor A. That's the different tenderizer treatments. Degrees of freedom is the number of tenderizer treatments, which is 3 minus 1, so 2 degrees of freedom. It's a fixed effect. And then that error term to test both blocks and the factor A against is that blocks by A interaction. It's random because it has a random piece inside of it, so it becomes random. And then at the bottom part of the experiment, within an orange block, we've got the B effect applied, and we can test the A by B interaction. Those are both fixed, and then we have the final bottom residual term. So this is actually kind of the experiment we had, but we're also looking at some of the other, we're looking at blocks by B and blocks by A by B as well. Okay, so maybe that helped a little bit. So let's look at that example. If I go to the JMP Help, there is a sample data library, and I know that this experiment is called split plot. So this is a terrible example to use with students when I want to ask them what the analysis or what type of analysis is appropriate, because it's right there in the name. So here we have the carcass, which is the block, the particular turkey. The tenderizer treatment, there's 3 of these, and the roasting times, there's 4 of these. If we want to really quickly just look at how many carcasses, how many tenderizers, how many roasting times, let's look at the distribution also. This is a really nice thing about using JMP. We can see that it's a balanced design, because as I flip through the 6 carcasses, we get the same distribution of the tenderizers applied and the roasting times applied. As I click through the tenderizers, same thing, roasting times, same thing. So you can see, obviously, it's a balanced design. We can also see some trends, like we can see that the longer roasting time seems to have these lower response values. So this has something to do with how tender or how, I think smaller numbers were a more positive rating on a rating scale. So longer roasting time for any of the tenderizers was a positive. We can see that this middle tenderizer seems to have the lowest values compared to vinegar or control. Okay, so if we wanted to analyze this, we'd go to Analyze, we would go to Fit Model, and again, if we're in standard JMP, we're going to use standard least squares. We'd use y as our response variable. Our carcass was our block, so we can add the carcass, but that becomes random. Our tenderizer is our factor A. Our carcass by tenderizer is the term that we're testing carcass and tenderizer against. Then we've got the roasting time as our factor B. It's fixed. We can look at tenderizer by roasting time. So the A by B interaction. And I think that's all we need. So blocks A, blocks by A, B, and A by B. So that should be our model here. So if I click run, we see this in the random effects predictions BLUP output. And if I go back to relaunching this analysis and we switch the personality to a mixed model, now we see these as fixed effects and random effects instead. So A, B, A by B, block, and block by A. So that's what ended up in this model. And if we run it from the mixed model, we get the same information, but in a slightly different format. Okay, so any last questions about split plot designs? And then we'll jump into PCA.
I think we're good.
Okay, wonderful. So if you do want to read more about examples of split plot designs or how to run them in JMP, the help documentation is really nice for this. So if you go to the JMP help, it's all online. And there's a chapter on split plot designs. It's going to use that turkey carcass example. So if I looked for a split plot, there's a split plot design example, split plot example. So if you find with different numbers of whole plots, simple split plot, repeated measures. So there's a lot of nice examples in the JMP help. So it talks about the whole plot treatment, the whole plot ID, the subplot treatment, the subplot ID. Those IDs are just the term of the experimental unit that I was talking about before. So it'll show you examples, it'll show you how to fit that example. So there's a lot of nice stuff in our documentation. Okay, I'm going to go back to our cotton example to look at principal components analysis. So let's open that again. So for principal components analysis in this example, I might want to find the, and you can see I actually did this before and saved out my principal components. Let's delete them now. So we can do this again. So I might care about reducing dimensionality of these 3 responses. So perhaps instead of predicting the length separately from this measurement separately from the strength, maybe there's something else. Maybe I would rather predict something about the principal components, or maybe I want to use the principal components to predict something else. So when I want to reduce dimensionality of many things that are continuous, then principal components analysis is a good choice. So I would find that under the Analyze menu, under multivariate methods. Multivariate methods, just multivariate, we can start there just to explore what the correlations are between these continuous response variables, or we can go directly to principal components, or we can do other things that have to do with multivariate analysis, like a discriminant analysis, partial least squares when you've got correlated predictors, structural equation models, factor analysis, and so on. But I'll start with multivariate just so we can see the correlations, and then I'll go to principal components. So I'm going to start here in multivariate. I'm going to ask for these three options. You can see I have different estimation methods. I'll go with the default, which is generally the best option depending on the type of data that we have. So I'm going to ask for, oops, I wanted this guy also.
Hi, Ruth. There was one question just on how this differs from a nested design.
Oh, the split plot, how it differs from a nested design. Great question. So in a way, a split plot design is, so you're nesting the split plots within the large plots, but you're re-randomizing within each of those, and you're re-randomizing things that are the same between the different components. So if a really classic example of a nested design is to think about doing an assessment of teachers, where you want to go within school systems, within classrooms in those school systems, and then maybe to different classes for each teacher within those classes, within those sub-school systems. So a nested design, typically as you follow the hierarchy down, you don't have things repeated down one line of the tree that you have in another line of the tree. So a teacher in one school system is a totally different teacher in a different school system. So teacher 1 in school system A is a different teacher than teacher 1 in school system B. So that's the nesting means that when something is nested within another category, it totally changes the meaning of that particular coding. Whereas a split plot design, you're actually re-randomizing the same things with, it's as though you take the same set of teachers and use them in one school district, and then you apply them in another school district at random to a new set of classrooms. So that's sort of the difference between a split plot versus a hierarchical or completely nested design. There is obviously nesting in the structure of a split plot, but you're re-randomizing the same fixed effect factor treatment groups. I hope that helps a little bit. If there are follow-up questions, feel free to type them. Okay, so for our correlations between length and strength and MIC, oh, I know, I was going to use uniform and I have it ignored. So I've got some coding in the data set. I forgot that I'd excluded that guy. So we've got 3 variables that we're looking at. And so first we just see the actual correlations. You see length with length is 1. Well, that's not rocket science. We're very pleased to see that we have 100% correlation with ourself. Same with strength and MIC with MIC. The off diagonals are what's interesting. So length with strength has a correlation of 0.83, almost 0.84. Length with MIC is only 0.4. So you can see that MIC is not as highly correlated with length and strength as they are with each other. And we can see that visually from this plot. We have a lot of options, like we could show density ellipses to show sort of how fat that circle is. If the circle's tighter, then that means like tighter correlation. So we can visually see this in a lot of different ways. We can actually look at non-parametric densities, which is cool. It's like hotspots, so we can see where the areas of most of the points are, or most of the density in that region is. We can ask for showing the correlations in the plots, so we actually see these. So there's a lot of cool things you can do here. If this is what you then want to take to publication, it's easy to save stuff out of JMP. One thing is this fat plus sign. You can just click on whatever component you want to keep and Control-C, Control-V, or copy-paste to remove this and copy it somewhere else. Or you can save this in a lot of other ways. You can go to File and Export, or File Save As. Save As is usually on the Windows. You're going to go to File Save As. On Mac, you'll typically go to File Export, and so I could save this as different image file types. I could save this as HTML or interactive HTML. If it's interactive HTML, then I can still keep this interactivity where I'm clicking on things and it's connecting back to the data table and it's connecting to the other plots. So that helps me explore if I see a point or several points that seem like they're outside of the range of the other data. I can see if that's true in all the other dimensions as well. Okay, so once I've explored the correlations, now maybe I'm ready to actually do the principal components analysis. So I now have that as an option. There's also an outlier analysis. So if you wanted to see multivariate outliers, this is a nice tool here. You could look at like Mahalanobis distance and you could see points above this dotted line are perhaps outliers in multivariate space. So all of these guys in here might be multivariate outliers. And you can see why they kind of fall outside of the general space of these paired scatter plots. But I can also go straight to the principal components. So I can do the principal components on the correlations, covariances, or unscaled. I think the default is usually on correlations. So I've added the principal components analysis at the bottom on correlations. I see that the first dimension explains 72% of the variation. 2 dimensions explains 22% more, but of course all 3 explains 100% because there's only 3 variables. So 3 dimensions didn't reduce anything, but 2 dimensions I can capture 95% of it. So I might choose just to save out 2 dimensions. So I can ask for the eigenvectors, the scree plot, loading plot, do this as a factor analysis, save principal components, even save the principal components with imputation for any missing data. So I'll save 2 principal components, and here they are. Now I could go, for example, to graph and graph builder, and I could look at this. Let's look at the strength as the response, and let's look at that against the first principal component. So we can see there's a high correlation between strength in the first principal component. Let's look at strength in the second principal component. So that's adding something a little bit additional. So I can explore a lot of things. That graph builder is a really nice tool. So this is typically how I would look at principal components, is first general multivariate and then moving on to principal components, but you can also go directly there by going to multivariate methods, principal components. You get default methods again, and the sparse is another good option. Let me show you an example with the sparse. So I'm back in the help menu. I showed you sample data library with just a list of data sets. If I go to sample data, almost the same name, I get this indexed list. So if I look at multivariate analysis, I can see this example here, adverse R split, is a good example of sparse PCA. So I'll click on that example. So what we have here is a bunch of 0, 1 variables. So they're coded as numeric, but they're actually just 0, 1. You had this adverse event or you did not have this adverse event. So we've got tons of zeros. So it's really sparse data. This is not something that you'd typically be able to do principal components analysis on, just a standard principal components, because you've got all these zeros and just ones as the alternate. But if we choose multivariate methods, principal components, and we choose the sparse option, we have to specify how many components we want. So I could ask for 2 or 3 or 4 or however many I want, and I can ask for all of these effects. So I use the shift key to grab all of them. If I had supplementary variables, I can include them here. And I say okay, and so now I see those 2 dimensions sort of appearing. So I can see which of those columns seems to contribute the most to these different dimensions. And I can see which patients seem to contribute most to the different components dimensions. And again, I can save out, I can look at the eigenvalues, eigenvectors, the loading matrix. I can save out or look at the scree plot and save out the principal components themselves, or the predicted values, or whatever it is I'm looking for. So that's how you do principal components in JMP and in JMP Pro. We've got a little more than 10 minutes left, so this is a good time, I think, to stop. And if there's anything you'd like to ask about, I'd love to show it to you.
Jermaine, did you have a question? You raised your hand. No, she doesn't. She just accidentally raised her hand. All right, does anyone have any questions? Okay, there's one. Can you elaborate on the eigenvalue and eigenvector?
Sure. So you're asking me about something that is not my strong suit as a statistician. This is not really my area. So we're going to get some help. This is a great time to use one of these tools in JMP. This little question mark, if I hover it over something that I want to learn more about, either because I don't know what JMP is doing or because I don't know myself what that topic is really about, I can use this. So we can click on this to get to the section about eigenvalues in the JMP help. And so it's going to talk about well, that's that section. Where's the actual eigenvalue? Oh, right up here. Okay, so the eigenvalues represent a partition of the total variation in the multivariate sample. If you chose the on correlations option, eigenvalues are scaled to the number of variables. And that's not telling us a ton about how they're calculated either. So I think maybe we would want to click on this reference, this 2003 paper, and so we could do that to track this down farther. The basic idea of both the eigenvalues and the eigenvectors is some kind of like a slope, like a coefficient associated with how strong that effect is. And so I'm not giving you the best definition of what that is. The statistical language you'd want to use around that, you'll want to look that up. But it's this higher the eigenvalue, the more variance that's being explained. So principal component 1 is explaining more with 4.8 as the eigenvalue than principal component 2. Let's look at the eigenvectors. So this is sort of like loadings on those principal components. So these are the vectors. And so abnormal vision, for example, has a high loading on principal component 1 and a lower loading on principal component 2. So we see those numbers. Some of these numbers are negative. So anemia has a small but negative loading on principal component 1. So if you had anemia, you're less likely to have a high value for principal component 1, but you'll have a moderate value for principal component 2. So that's, let's look at so here's the list of the eigenvalues again for principal component 1, principal component 2, and the singular values that are associated with those. Sorry that I can't give you a better, more statistical answer to that, but they're basically how important, and the eigenvectors are showing those loadings.
Ruth, we have another question.
Sure.
Can you show quickly the best way to save scripts for reproducibility of data analyses? And on
Absolutely.
that, someone else asked me a question on, can you go between SAS and JMP?
Sure, yeah. Okay, so first, saving scripts. So I've done something in JMP. I did this principal components analysis with sparse PCA. I asked for eigenvectors, I asked for eigenvalues, so all of this stuff is in my report. And this is the report I want to save. I can go to the top red triangle and save script to data table. So this is a really nice way to keep all of your scripts, everything you've done, just saved back in the data table. So if I do this, save script to data table, it prompts me to give it a name. Principal components make sense. So I'll close this, and now back in the data table, there was already something called principal components, so I had to call it principal components 2. But now if I click on that, it repeats what I did. So now I can unhide the eigenvectors again, or hide them back, or unhide the eigenvalues output again and hide it back. So anytime you do something in JMP, just go to the top red triangle, save script to data table, and that saves the script for repeatability right here. So then just make sure you save your data table again so that that's sitting there. Every time you open it, you can go back to what you did. This is really good practice just as you're cleaning data. So maybe the first thing I do is go to Graph Builder and explore the relationship between alopecia and abdominal pain, and I pick some better way of looking at this. So maybe I make some kind of a plot, and then I save script to data table. So everything I do, I just keep saving all my scripts to data table in the order that I'm doing them. If I decide I want to change the order, I just move things around by dragging, and then save it in the data table. But the other option is, if I've done something and I don't just want to save it to the data table, I want to save it another way, you can also save it to a journal. And I didn't have a journal open, but that's just like a blank place where you can put text and you can put hyperlinks. So now it's a hyperlink that takes you back to the output. So there's other ways to do this too, but the one I'd recommend is just save to data table. And then about using this with with SAS. So you can connect JMP and SAS really easily because we're the same company. So there's a lot of built-in ways to do that. You can also use JMP with CAS, the Cloud Analytics Services commands from JMP or from SAS. You can also use JMP with R and with Python and with MATLAB. There are connectors for all of these things, but the connection with SAS code itself is the easiest one because, again, we're the same company, so it's kind of built in. So let's say you went to Fit Model, and let's use our cotton example again. So here's our cotton data. I go to Fit Model, and I try to fit a model predicting strength from genotype and sample method, and genotype by sample. Right now, I can go to the top red triangle and I can choose create SAS job or submit to SAS. If I have a SAS connection set up, it will submit it. Right now, it just gives me the code that it needs. So it says, here's the data. You needed sample, genotype, and strength in order to run this model. So here's that subset of the data in a data step. And then here's the proc GLM to run that particular model. Sample and genotype are class, classification, strength equals genotype, sample, sample by genotype. So it's a pretty simple model so far. So you can trick JMP into writing some SAS code for you if you're writing a simple model. But as soon as you get into random effects and other more complicated things, there's too many different ways the SAS code could be written, so you won't find that option anymore. If I switch to a mixed model, for example, you no longer see that choice to submit to SAS or to write the SAS code. So when you want to write some SAS code out, leave it as a standard least squares, write a simple version of the model, and then you can go in here and edit. So now I could put a random statement in.
There's another question following up on the previous one that says that if they added new data, another year of data, will it add to the saved script?
Yes, so as long as you add the new year of data in your data table, that's my wrong data table. So if you add a new year, so you go to the bottom of the data table and now you put in 40 more rows with a new year, all of your scripts would get applied to the new data the next time you run them. So if you're saving the scripts, you're actually saving the ability to rerun the model. If you wanted to only save output, then you might want to save it by saving it as images or something else instead, something static. But these scripts are actual scripts that will rerun on all of your data. So if you add a totally new variable, your models don't refer to the new variable, so they wouldn't get used. But if you just add another year within year, that's going to be run into your next model the next time you run it. A last thing about the SAS connection, to set that up, under File, there's a SAS option. So you can set up a server connection if you've got a SAS server that you're able to access, or I think with a server connection, you can also use SAS on demand for academics if you're an academic and have a SAS on demand for academics account. So either a server connection or SAS on demand for academics. There are some nice help documents on this at our jmp.com/learn. There are a number of, about 94, I think, one-page documents that just help you with very common things you might want to ask about in JMP. So as we slowly go there, there's a section on using SAS from JMP. And so if you click on that, it'll help you setting up your SAS server connection. There's also a section on mixed models and repeated measures, data mining, predictive modeling. So if you want to know how do I do this thing in JMP, there's probably a page that tells you about it. So if you want to make a classification tree, there's a 2 to 3 minute video and a 1-page guide that talks you through how to do those things. Any other questions?
Do you want to spend a second telling them about the new graph builders, add-ons in the JMP 15 that I went to the webinar for? Or do you not have JMP 15 here?
I do have JMP 15. So one new feature in JMP 15 is that now you basically get distribution output at the very top with this little guy here. So that's nice. Where's that cotton data again? So if I expand this, I now can see the distributions right here and everything's interactive. So I can look at 2010 versus 2011 versus 2009 for the length. Then when I go to graph and graph builder, there are some additional features. If you haven't used JMP for a while or you aren't a JMP user, there's the ribbon at the top gives you lots of types of graphs that you could look at. So I might look at the length of the cotton plants based on the genotype. And I might decide to connect the means, and I might want these as box plots, and I might want to split it out by sample, or group them by sample this way, or wrap by sample, or overlay by sample. So I kind of just hover around to find different options. Then within each element, there's more tools for editing that. So for example, I could jitter the points differently. I could have no jitter, so they're just all in a stack. I can't tell where the hot spots are, I could put a density ellipse on, so a violin plot to see the density better. For the line, I could ask for error bars associated with that. For the box plot, I could ask for a different type, a quantile box plot instead of an outlier box plot. So everything has sort of sub controls down here. For the contour plot, I can do the smoothness more or less. Yeah, there are videos. If you have been a heavy JMP user and you just want to know the specifics of some new things, there are some videos on the JMP website, so jump.com. If you search new in 15, you'll find some videos specifically about the newest features.
I think that helps a lot. Any more questions? Oh, someone just asked, fixed or random effect, easy way to distinguish. I can't tell what that.
Yeah, so my recommendation would be to think about, do you care about making comparisons between the levels of the variable? So if it's year and you've got 2009, 2010, 2011, do you care about comparing 2009 to 2011 because you specifically care about those years? Or do you just want to explain variation between the years and you really wish that whatever's true about the genotypes is true in 2015 as well, that it's not specific to the year? So when you're trying to just explain variability, random effect. When you really care about the specific levels, they really matter. You care about this genotype versus that genotype, and you don't want a different genotype subbed in, then it's a fixed effect. There's a little bit of nuance to all of this. There's some different things you get by treating something as fixed or something as random, but pretty much it boils down to, do you want to make comparisons between year 2009 to 2010 because that's the primary interest of year, or is the primary interest of year that there will be variability from year to year? You'd certainly like to see if a year is really bad, but you don't care specifically about comparing the years to each other. You don't need to know which one was the best year. So if it's about variability and just explaining it, then it's random. If it's about, I want to make comparisons between this one to that one, and I only care about these, they're not a sample of any possible year, it's only these years I care about, then treat it as fixed.
Well, I guess that's all the questions. Thank you so much for answering them with so much patience and going over all of the detailed statistics and JMP functions with us. Yep, that's it. That's all the questions, Ruth. I think
Wonderful.
we didn't get into much more of your time.
Yeah, no problem. Again, as last time, if anyone would like to email me directly, you are welcome to. I'll put my email up on the screen. Oops. Let's try to find a sticky note. And you are welcome to send emails if you've got specific questions that I wasn't able to cover, or if you want to know how to get JMP. If you're an academic, it's pretty inexpensive or possibly even free, and so certainly get in touch with me. If you are commercial, it's competitively priced, and so we'd certainly be happy to get you connected with the right folks if you're interested in using JMP or getting a trial version of JMP.
Perfect. Thanks a lot, Ruth.
You're very welcome.
All right. Well, we're calling it a day. Thanks.
All right.
Bye,
Sounds
everybody.
good. Bye-bye.